Hello, welcome again. So in today's lecture we will be discussing about the next topic, which is back bonding. So in this topic we actually see a type of bonding in which an electronegative group is attached and an electron deficient or the empty p orbital is present here, and this fluorine has more electronegative element. It has more electronegative element and it is the most electron withdrawing group, so it will attract the electron density back from the boron and donate this into the empty p orbital of the boron group. So this is called back bonding. So now let's discuss its definition, what happened in this process. So this is the process that is happening in back bonding process. Here BF bond is a polar bond and fluorine is more electronegative and has electron density attract toward itself the attracted electron density of fluorine. Okay, then this fluorine itself electron density start to repel due to inner electronic repulsion, the repulsion between the more electronegative and the density which is coming from boron. So the repulsion will be more in fluorine molecule. This repulsion insists fluorine to donate electron density by a pi bond back into the empty p orbital of boron. So this is called back bonding. There are some conditions for back bonding. Let's see one by. So these are the conditions. First, the bond should be polar. So polar bond must be present. This is the first condition. And in second condition, one atom should have vacant orbital and the adjacent atom should have lone pair. This is the second condition, an important condition here. And third one, for better back bonding, one atom should be from second period and adjacent atom should be from second or third period. Then only the back bonding is possible. So let's take an example. Let's discuss about this A and B. These are the molecule, and A is from second period and B is from second period. So it has the best back bonding. And again, if A and B, one is from second period and this is from third period, then here back bonding is possible. And now let's discuss about the second period and fourth period. So this is the order of back bonding, or it has the best back bonding and it has the least. And if A and B, if one of the group has third period and this B is from the it is also from third period, so there are no back bonding. Here we do not see the back bonding. Back bonding is not possible in this molecule, this type of molecule. Now here are some examples in which we can see the back bonding, such as BF3, BCl3 and OCl2. Oxygen has a lone pair of empty d orbital and chlorine has can donate, and nitrogen SiH3 thrice. This is also has empty lone pair from nitrogen and will donate from silicon empty d orbital. And another example that can be seen is oxygen and silicon H2. And this is an example in which back bonding can be possible. So the first application of back bonding will be effect on back bonding, effect on bond length and bond order. So let's take an example of BF3 and BF4 minus. So if we talk about the hybridization, it has sp2 hybridization and it has sp3 hybridization. And if we talk about back bonding, then back bonding is possible in BF3 molecule but not possible in BF4 molecule because BF4 minus molecule, because it do not have the vacant d orbital. And if we talk about the bond order of BF bond, then bond order of BF BF3 is greater than as compared to BF4 minus, and the bond length comparison of BF3 as compared to BF4 minus will be inverse, or this will be greater. So the next application of back bonding will be effect on hybridization, geometry and shape. So as we see that if we talk about back bonding in one case, this is the case 1, this is case 1. So in first case, the side atom, in side atom the electron density is just like in BF4, BF3 molecule. We have seen this type of donation. The central atom will get the donation from side atom. So this fluorine will be side atom and it will donate the electron density from the lone pair to empty d orbital. So this is the first case where back bonding is possible, and here no change in hybridization when back bonding is possible. And in this case, in case number 2, the example of NiC3, this is the example of back bonding in which nitrogen donate m orbital from nitrogen to silicon. So this is called the central atom to side atom donation, and here the hybridization will be changed after donation. Now let's discuss about the next topic, which is Lewis acid and base. What are Lewis acid and which are Lewis base? So the Lewis acid are those who accept the electron pair are called Lewis acid, and those who donate the lone pair are called base. And the back bonding is inversely proportional Lewis acidity and directly proportional to the basicity, Lewis base. Some example of Lewis acid such as BF3, BCl3, BBr3. These are example of Lewis acids in which the fluorine will donate electron and this boron will accept. These are the example of here. The Lewis acidity, the order of Lewis acidity will be this. And if we talk about the order of back bonding, it will be inversely proportional to this order. So BF3 has highest as compared to BCl3 and BBr3. This is the order of back bonding. Now let's get back to the next topic, which is Fazan rule. Fazan rule. According to this rule, let's consider AB, in which it is a, before knowing the Fazan rule, let's discuss about the covalent character or ionic character. What is covalent bond? So here the percent ionic character is depend upon dipole moment and electron negativity. Let's discuss about the another example. And if the bond is ionic bond, then it will tell us about the covalent character. This will give about the percent ionic character, and this give information about the covalent character, and we can discuss Fazan rule here. So Fazan rule help us to calculate the qualitative, so it will give the information about the quantitative analysis of covalent character. So what is the crux of this Fazan rule topic is that charge, if the charge is increasing in the molecule, then smaller the cation and larger the anion. So these are the Kazan rule in which we will be discussing about. Now let's discuss about what is a polarization. So more the polarization, more will be the covalent character. More polarization, more will be the covalent character. So this is the important point. And the polarization power of cation is the tendency of cation to distort the anion, or polarization power of cation is directly proportional to charge and inversely proportional to the size of cation. So polarization power of cation is the tendency of cation to distort the anion, and polarization power of cation is directly proportional to charge and inversely proportional to size of cation. And the next, which is polarizability of anion. So it is the tendency of anion to get polarized, means, and it is polarizability of anion is directly proportional to the anion, and it is also directly proportional to charge, and it is directly proportional to the size of anion. So here are some questions. Let's discuss one of them. According to which compound with maximum ionic character are first NaCl, second CSF, third CSI, and fourth NaF. So this question, the maximum ionic character. So what is the ionic character? So it is the minimum covalent character. So if the compound has minimum covalent character, it has maximum ionic character. So for minimum covalent character, the large cation will prefer and a smaller anion is preferred. So in this molecule, this has the larger cation and smaller anion. So this is the final answer here. As you can see, this is from the 6th period. So it is from the 6th period, and this is from 2nd period. So it has large cation and small anion as compared to all these. So this is the final answer. Now let's discuss about the next important topic, which is dipole moment. So it is a vector quantity. It is a vector quantity. So in this dipole moment, we can discuss polar and non-polar in the first category and percent ionic character in the second category. So what is dipole moment? If we consider this is a molecule, and if this is a ionic character, if this A has positive, partial positive, and this has partial negative, so the direction of dipole moment will be like this. And this is the symbol of dipole moment. This plus sign and this arrow denote the dipole moment. So if a molecule mu net is equal to 0, which means it is a non-polar molecule, and if mu net is not equal to 0, if the value is come, so it is a polar molecule, and we can discuss dipole moment in this type of molecule. Let's discuss some example of dipole moment in molecules such as BF3. So this molecule has dipole moment or the net dipole moment, one going from this mu here and this mu here and this mu here. So the resultant of this mu will be in the back side, and this two cancel out each other. So it do not have the dipole moment or mu net which is equal to 0. So it is a non-polar molecule. It is a non-polar molecule because net dipole moment in this molecule is 0. Now let's discuss about the PCl5 molecule. PCl5 molecule. So here the net dipole moment is also 0. Why? Because this direction, this is in the plane and this is from up and down. So this mu and this is mu1 and this is mu2. So this cancel out each other, and if this is mu1, this is mu2 and this is mu3, so this mu1 is equal to the resultant of this molecule. So this will also cancel out each other, and the resultant will be here mu net is equal to 0. So it is also a non-polar molecule. And let's discuss the polar molecules such as PCl2F3. So in this molecule the structure will be this is the structure. So here it has a mu1, so it will cancel out each other. So mu2 and this is, let's say, mu2. So these mu2s will cancel out each other, and this mu1 is not equal to this mu2 or mu4, let's say. These are mu4 for chlorine molecule. So it is not the resultant which is cancel out each other. So mu4 is not equal, will not cancel out this molecule. So this is a polar molecule. Here mu net is not equal to 0. So it is a polar in nature. Now let's get back to the next topic, which is percent ionic character. So for calculating the percent ionic character, we have the formula, which is mu observed upon mu experimental upon mu calculated upon mu theoretical into 100. So this is the formula for calculating the percent ionic character. So there is one question. According to this ionic character calculation, the observed dipole moment of LiH molecule is this, and the LiH bond length is this. Then we have to find the percent covalent character. So we know that the mu theoretical is equal to Q into D, and by putting the value of this 1.6 into 10 to power minus 19 coulomb into 2, what is 2? This is the bond length, into 10 to power minus 10 meter. So by solving this, 1.6 into 2 to 10 to power minus 19 into 10 to power minus 10 meter. So the value will be 3.2 into 10 to power minus 29 coulomb meter. So this is the value of mu theoretical. So we put this value in the formula that we know, which is percent ionic character is equal to mu observed upon mu experimental upon mu calculated into mu theoretical into 100. So we know the value of this and this. So 1.7 into 10 to power minus 29 coulomb meter upon 3.2, which we have calculated just yet, into 10 to power minus 29 coulomb meter into 100. So this will cancel out each other. It will cancel out, this will cancel out each other, this also. So we will get the result of 1.7 upon 3.2 into 100. By solving this, we will get the 53.125%, and this is the ionic character. So we know that in a molecule the ionic character plus covalent character form the total molecule. So for percent covalent character we need to minus 100 minus 53.125. So we will get the result of 446.875. So this is the final answer that we will get in this question. Now let's discuss about the last part of this chemical bonding series, in which we will be discussing about the molecular orbital theory. So this theory is very important, and so many questions are can be studied from here. So it is based on the LSEO theory, which is linear combination. What is LSEO? It is the linear combination of atomic orbitals. So what will happen in this MOT theory is, when two atomic orbitals undergo mixing, then two molecular orbital will form. First will be bonding. First molecule that will be formed here will be bonding molecular orbital, and the next that will form is anti-bonding molecular orbital, just like as we can see in this diagram. There is one atomic orbital, this is one atomic orbital. When this combine to form the two new atomic orbital. So these two new atomic orbital, as you can see, are bonding molecular orbital. This is atomic orbital and these are bonding molecular orbital, and this is anti-bonding, or ABMO in short, anti-bonding molecular orbital. This type of orbital will form here. So for better mixing, the energy gap between the atomic orbital is less and should have been identical, symmetrical. Now, as you can see from this structure, if the gap between this molecule are less, then the easily the anti-bonding and bonding molecular orbital can be formed. So if the A2, in case of A2, the atomic orbital and this atomic orbital are in the same plane, so in the same periphery, same plane, so it will the bonding and anti-bonding molecular orbital will be near or close to each other. And in second case, a B type of molecule, if one has greater and this has greater energy and this has less energy, so this type of structure is formed where the distance between these is a little bit greater. But in case of when delta E or the B is very greater as compared to delta atomic orbital of A, so what will happen here will be, this will go into the non-bonding and this will also go with the non-bonding and do not form the hybrid orbitals, or these are hybrid orbitals. So what are molecular orbital? Next that we discuss here will be, what are molecular orbital? So molecular orbitals are such as sigma 1s, sigma star 1s. This is for bonding and this is for anti-bonding. This also from sigma 2s and sigma star 2s. This is bonding and this is anti-bonding. And the sigma 2pz or sigma star 2px. This will form due to the head-to-head mixing. And sidewise mixing, the orbital that are involved in sidewise mixing will be pi 2px pi to py and pi star to px, pi star to py. So as we can see, this is 1s and this is 1s orbital, and if the constructive interference is occur between these two molecules in the same phase में combine होंगे, then this will form sigma 1s. This is the structure of sigma 1s orbital. And for let's discuss about this some properties, such as sigma 1s is bonding molecular orbital. It do not have any nodes, and center of symmetry is present in this molecule, and it is G-red in nature. Now let's discuss about the anti-bonding of the sigma star 1s, or in short sigma star 2s. It has a little more big size as compared to first. So what will happen here is, if the phases are different, just like it has positive and this has negative, so these will form a destructive interference. So if the molecule form destructive interference, then this type of low double shape will form in the hybrid orbital. So it is anti-bonding molecular orbital. It has one node and center of symmetry is absent here because one phase is positive and negative, so it do not have any center of symmetry, and it is ungirate in nature. Now let's discuss about the third type of orbital, molecular orbital, which is sigma 2pz. Z-axis considered as internuclear axis. If you consider Z-axis as internuclear axis, what this means is that we will consider this x, this y, and this is the Z-axis, in which we will consider it as internuclear species. Now let's discuss about the here also the constructive interference occur between these two orbitals, and it will form sigma 2pz orbital. It is also bonding molecular orbital, and the center of symmetry is also present here. It do not have nodes, and it is also G-red in nature. Now let's skip about the destructive interference of the sigma star 2pz orbital. It is also, the structure is just like this, sigma star 2pz, and it is an anti-bonding molecular orbital. One node is present, center of symmetry absent, and ungirate in nature. And for pi 2p orbital, it has this type of sidewise overlapping. If the constructive interference occur in this 2px or 2py or 2px or maybe 2py, then this will form 2p pi 2p orbital, and this is just like this shape. So if you talk about bonding molecular orbital, it has bonding molecular orbital. It has one node, center of symmetry absent, and ungirate in nature. And the last one, which is pi star 2p, and here destructive interference is seen. And why destructive interference? Because it do not have the same phase. One is plus, one is minus, and the same from here, and it will form this type of molecule, this type of orbital, and it is anti-bonding molecular orbital. Two nodes are present, one from this and one from this. Two nodes are present here, center of symmetry present. Why? Because this is positive and this is positive. So if we go inversion, if we check inversion, so it is center of symmetry present, and it is G-red in nature if the center of symmetry is present. So let's discuss some summary. So these are all the orbitals and their nodes, center of symmetry, and G-red or ungirate. Now let's discuss some of the homonuclear molecular orbital diagram, in which we will see about the no sp mixing in, and some has sp mixing. So these molecule in the left has no sp mixing, and these molecule from the right have sp mixing. So when we will see the sp mixing and when we can't see the sp mixing is depending upon the number of electron. So if the number of electron is greater than 14, just like in O2 F2 O2 F2, then a sp mixing will be shown. And if the total number of electron is less than 14, just in case of B2, C2 and N2, So this type of orbital are involved here. So the only change that is occur in the molecular orbital diagram will be the position of these orbitals will be changed. These orbitals will be interchanged from each other in the sp mixing and in another case. So here are the example of H2. This is the MO diagram for H2, as you can check, and there are some questions, as you can see, easy question, you can read it. Then let's check about the helium 2 molecule and their molecular orbital. So this type of van der Waals interaction has been seen because no bonds are formed here, no existence of bond, so only van der Waals interaction is formed in this molecule. Here are some example for van der Waals interaction where no existence of bond or bond order is 0 in case of these molecules. So the molecule has 4 electrons, then its bond order is 0. If the molecule has 8 electrons, it is also 0, and for 20 electrons it is 0. Now let's discuss about the lithium 2 molecule. So it has a sigma bond. How we will describe? So what is bonding orbital? So for calculation the bond order, we use a formula which is 1/2 bonding molecular orbital molecular orbital minus anti-bonding molecular orbital. Number of electron in these two will give us the bond order. So in case of lithium, the bond order will be 1. So one bond is present in these elements. Now, so as you can see, now let's discuss about the next bond order or the next molecule, which is beryllium 2. So as you can see, its molecular structure is this, and in B2 sp mixing is occurred. Why? Because it has sp mixing is possible here because sigma 2pz will go upper in this case, and here in case of C2 both pi bonds are present, both pi orbital are present. So as you can check here, it is the two in carbon, between two carbon, two bonds are present. So it is a diamagnetic molecule. Why diamagnetic? Because there are no unpaired electrons in the molecular orbital. And here in case of N2, it is also diamagnetic in nature, and it is homo, and its highest occupied molecular orbital has sigma 2pz or sigma g rate, and its LUMO has lowest unoccupied molecular orbital and pi star 2p, which is pi g or pi g rate. And if we calculate the bond order of this N2 molecule, we will get the bond order will be 3. So as you can see, it has 3 bond. Now let's check about the next, which is O2. Total number of electron of O2 will be 16. So it has no sp mixing. So if we have checked as in previous slides, if a molecule has greater than 14 electrons, so it do not have sp mixing. So the order will be in this, and in case of sp mixing, the order will be like this, and here this. Sigma 2pz will go down. In fluorine, it is also do not have sp mixing, and total number of you can check here. Now what is the trick for calculating the bond order or the molecules? So this is the trick, you can check it out. The total electron से bond order निकालेंगे, then we will write down 14 electron, 15 electron, 16 electron, 17 electron and all that, and after that we will check the bond order. So this is the bond order, and we will see the N2, O2, F2 and N2 will be present here. Now let's discuss about the homoatomic molecular orbital, heteroatomic molecular orbital, which means we will discussing about the homoatomic. Now we will discuss about the heteroatomic, means two different elements are present, just like in HF there the molecular orbital of HF will be like this, and it is diamagnetic in nature. Why? Because number of unpaired electrons are present, and if you calculate the bond order in this molecule, then it will be 1. There one question, which is the HOMO of HF is non-bonding. As you can check, the HOMO, highest occupied molecular orbital, is non-bonding. Why non-bonding? Because this is the structure that we need to remember. In case of OH, as you can see, it has a bond order of 1. In case of CN, it has a bond order of 3, and this is the molecular structure of the hemodiagram. And in case of NO, the hemodiagram is like this, and it has a bond order of 2.5. So here, and next will be CO, carbon monoxide hemodiagram, as you can check from here. And the characteristic of CO hemodiagram, coordination hemodiagram, in which HOMO is equal to sigma non-bonding, 2 mole is equal to pi star, which is CO in pi acceptor ligand. Bond order is CO and 1. Bond order is this. So this will be the chapter. Thank you.